hello to everybody. Our objective was to examine emergence of signaling conventions in a framework of multi-agent reinforcement learning model, and the results showed, to summarize, firstly, it is the network of interactions between agents that plays a critical role in achieving consensus. And next, the ratio of the number of words to the number of objects can also be an important parameter in the evolution of the system. And finally, forgetting, which we obtained by means of a population renewal, also considerably enhances formation of an efficient signaling. If we assume that language is a set of conventions shared by a group of users, which emerges from local interactions between them, we need to find a model explaining how a large number of individuals can agree on such conventions without any global control. There are also other phenomena such as opinion formation on or ferromagnetism, which have already been studied as emerging spontaneously via processes with so-called agreement dynamics. And models with such dynamics are often simulated using multi-agent systems, which enable us to examine how a language or voters' decisions or magnetization emerge in a population in a bottom-up fashion as a result of interactions between agents. We can mention here some models like Ising model, voter model, Moran, or naming game. And one approach considers language as a signaling system, which emerge in a reinforcement learning process, and such a framework originates from Lewis' signaling game. In the simplest version, there are only two players and a fixed number of signals. The sender sends a signal, the receiver interprets it, and if he does it correctly, both players receive some payoff. There are many versions of this game, and in most studies, the examined number of agents was rather small, from 2 to maybe 30, so we could use perhaps much larger populations in the context of language evolution or something. And then the network of agents' interactions has to be specified, and for a small group, maybe a complete graph where each agent interacts with each of the others seems the most natural topology. For larger groups, some other structures, such as regular or heterogeneous graphs, can also be relevant. The structure of the network usually plays an important role, determining whether the consensus will be reached at all, and affecting the way it could be reached. The reinforcement learning here is in fact equivalent to a Polya-Ern model. In its basic version, a ball is drawn randomly from an urn with balls in two colors. Then this ball is put back into urn along with an extra one of the same color. And this is the reinforcement. And the process is repeated infinitely. There are also many versions of the basic scheme. In other words, I can say that we studied a multi-agent model of a signaling game with interacting urns as agents, not talking heads, but rather talking urns using balls as signals. Agents may try to establish a name for one object, as usually, for example, in the naming game is done, but they can also negotiate simultaneously names for several ones. And let's start with a simpler version. Each agent here has an inventory of the same words coupled with their weights, initially all equal 1. And in an elementary step, a randomly selected agent interacts with one of its randomly selected neighbors, communicating a word. The speaker selects this word with probability equal to the proportion of its weight to the total sum of weights possibly raised to certain power. After the interaction, both the speaker and the hearer increase their weights of the word by 1, and such steps are iterated. This is a simple example of such an interaction. Each agent has the same 3 words. Speaker chose the second word, and both agents increase their weights of this word. So again, you can think of an agent as an urn. Words play the role of the balls of particular colors. A weight corresponds to the number of balls of a color, and increasing of weights implements the reinforcement learning. It means that there is a positive feedback. The more often a word is used, the greater is its chance to be used in the future. We analyzed the behavior of our model for several interaction networks, for Cartesian lattices, complete graphs, and random graphs. And for example, for the 2-dimensional Cartesian lattice that is read like this, the results of our computer simulations indicate that the model gets stuck in a disordered structure where consensus is only local. These 4 squares show the states of the system at various moments of its evolution. And you can see that even in the last one, there is no global consensus in the population as to which word to use. Global consensus would be all square in one color. It's not the case. However, since finally the probability of using the first word is generally close either to unity or to 0, as we have only 2 colors here, black and yellow, it means that almost every agent developed a strong preference toward one of these 2 words that are in use here. That is, most of the agents reach a monopolistic, a mono-word regime, and communicate with their neighbors with the same word. But this consensus is only local, as represented by clusters of the same color. Initially, such clusters do coarsen, but their evolution gets trapped in a disordered state much before reaching total agreement. And results for the 1 and 3 dimensional Cartesian lattices show a similar behavior where much different is seen for a complete graph, where basically all agents communicate using the same word. Not surprisingly, perhaps, full connectivity favors a global consensus. And we also examined the behavior of this model on heterogeneous networks, and for random graphs dense enough, with the number of links between them large enough, the model quickly reaches a global consensus as on a complete graph, while for smaller degrees of networks, the model remains trapped in a disordered phase, like on lattices. And maybe more interesting is a generalized version that is a multi-object model, where the agents try to establish names for a set of objects, not only for one. Now their inventories contain for each object the same set of words, again with weights. This time, speaker first chooses randomly an object he's going to talk about and selects the word for it with the probability calculated similarly as before. But the speaker now has to assign an object to that word. And the word appears in its inventory once for each object, always with the corresponding weight. And the hearer uses these weights to guess which object the speaker is talking about. And only if the object recognized by the hearer is the same as that chosen by the speaker, they succeed, and both agents increase their the weights of this word communicated by 1. So now an elementary step of the model looks like this. There are 2 objects, and 3 words in the system. Hence, each agent remembers 6 weights corresponding to all possible associations of the words with the objects. And here the speaker chose the second object, the big circle. Next, based on the 3 weights of the words for this object, selected the first word and transmitted it to the hearer. And now the hearer considers 2 weights of this word as it occurs twice in his inventory, once for each object, and on the basis of them tries to recognize the object referred. Again, on a square lattice, the model gets trapped in a disordered configuration where only some, not much, local consensus appears, rather poor, apparently. But on a complete graph, a much better consensus is reached. During simulations, we measured a success rate defined as a fraction of successful communication attempts, and numerical results for 10 objects show that when the number of words in agents' inventories is large enough, say 50 or 70, see the red and green lines in the figure, the model reaches rather fast the maximum success rate, but for smaller number of words, 20, 30, 40, these are the blue, pink, and navy lines, the success rate is much lower, even after long simulations. Yet another indication that the dynamics for large and for small numbers of words considerably differ can be found in the next figure, where total weights associated with words are presented. Here, a total weight for a given word is a sum of all its weights over all agents and all objects. So it can stand for the currency of the word in the population. For 10 objects and 50 words, we can notice in the top panel exactly 10 peaks corresponding to the 10 words that are mainly in use. And again, the number of objects is exactly 10. Taking into account a very large success rate we have seen in the previous slide, it means that the agents established a single word for each object, which became dominant in the population. And the resulting language provides a nearly perfect one-to-one mapping between words and objects. And let's emphasize that such a global, efficient language emerges spontaneously as a result of 2 agent interactions only. However, much different behavior can be seen for smaller number of words. In the bottom panel, for 30 words, some peaks can also be distinguished, but clearly there are also other words used by agents. The one-to-one correspondence between words and objects is missing in this case, and the resulting language has a much smaller success rate. Obviously, there are synonyms in this language, because also non-dominant words lead sometimes to a correct recognition, as they have non-zero weights. And there are also homonyms, words with significant weights associated with more than one object. Communicating such a word may result in an incorrect recognition of the object, and the success rate smaller than 1 indicates that homonyms are also present in the emerging language. And some intermediate scenarios are possible here too, where agents may develop a one-to-one relation between words and some objects, while with respect to some others, they use synonyms and homonyms. And as we have seen previously on a 2-dimensional lattice, both the single and multi-object versions of our model get trapped in a disordered regime with only a local consensus reached. Let us notice that in EARN models, due to the accumulation of weights, it is almost impossible to shift their balance here to change the language after a large number of iterations. But a simple modification seems plausible here. That is a population renewal or generational turnover which would make such a shift possible. Namely, with some small probability, the agent selected to be a speaker is instead replaced with a new agent with all its weights initialized again as 1. And now the time evolution of a single object model is different than in the absence of such population renewal, as the dynamics does not get trapped in a disordered state, and clusters of agents using the same word grow steadily. And also a multi-object model behaves differently in this case. We have already seen the left panel, and the right panel represents the results of simulations with exactly the same parameters except for the non-zero probability of a population renewal. And also it is extremely small. It causes the system not to get trapped in a disordered structure. Instead, we can see the coarsening of clusters. And also, this diagram has already been shown for a multi-object model on a complete graph. This time we can pay attention to the black line and compare it with a pink one, which clearly shows that even a tiny renewal probability considerably increases the success rate of communication, even for smaller number of words, here for 30. So this is a summary of. We showed that lattice topologies inhibit conventionalization, while complete or sufficiently dense random graphs promote establishment of lexical conventions. In the multi-object model on complete graphs, an efficient global communication may be established such that all agents unambiguously match each object with the same corresponding word. And our simulations also suggest that unique word-object matching may emerge only when the number of words is considerably greater than the number of objects. And if this is not the case, the resulting communication is less efficient, and the emerging language contains some homonyms and synonyms. And also the population renewal enhances emerging of an efficient communication as it basically resets the agent's weights, and thus it plays a role similar to forgetting, which is a factor known to improve the performance of reinforcement learning systems. And last remark, population renewal supplies new language users. Like children, they quickly learn a language of those they interact with, and let's notice that some linguists advocates the view that children play an important role in the process of language change. But such a view is perhaps not generally accepted, but I think it would be certainly interesting to consider an age-structured version of our model and analyze the role of the young generation in more detail, a possible emergence of its specific dialect and its influence on the language of adults. So that's it. Thank you for your attention.